Good. So as a multimodal task, normally it's usually used as a text base for evaluation of reasoning and generalization skill for AI models. So here's some features about VQA. As a complex reasoning task, it's demands a holistic comprehension of the scene. For example, on my left, we see what is on the wall. It's like they start the body object like next to the girl, so it would be easy for us. But you can the model can say painting and other answers, because it's a natural language task. It's allowed a broad spectrum of acceptable answer. For example, on the right and on the left here, what is happening? Someone can say people is watching videos or showing phone. It shows the complexity of the task. So maybe what you saw in literature is that complex data can benefit for the complex task. So we saw great effort towards scene graph for visual question answering. So instead of use the image, models start using scene graph. That in scene graph, nodes represent the objects in the scene, and the objects are connected by the relationship in a semantically and spatial way. So, for example, girls next to the tray and so on. And when ideal, we saw that the model benefits from this ideal information, gets some great performance. For example, GraphVQA here, getting 94% on GQA dataset. That's a complex dataset, overcoming even human on the same dataset. It's like it's skeptical, but it's like it show how ideal scene graph it's good for the test, could be good for the test. But when test with extract scene graph, we saw a decreasing performance going to 29%. So this came with our first, however, despite the great performance, when in real world, scene graph would be labor intensive to and expensive to annotate. Also, because it's information derived from an image, maybe one image can have a lot of semantic correspondence in graph. And also, when you use scene graph for a specific task, you should have some linguist base or some base on the scene graph, because like the scene graph, you always have the correct answer, the correct object for that task. So it's like a bias. So in our approach, we decided to be more practical. Instead of using the ideal scene graph, try with generated scene graph here. And also with a GNN-based model to try to take the math information from that graph format. And now, as ever, we are using a generative model. It's easy to liberate self-supervised learning. What you saw here is that the self-supervised learning improves our results with this non-ideal scene graph by enhancing the visual information. So our methodology. So inspired by the CMS architecture, we just try to maximize the information using some generic cosine distance between the unmodified and modified scene graph. So as we're handling with scene graph here, graph format, we try three distinct maximization strategy: local similarity, global similarity, and the self-scene similarity, which is a regularization for the permutation equivariance problem on graph. So this is like the naive approach, the common approach when you're dealing with scene graph, you just try to maximize the information, say to see if the models pay attention more on the objects in order to answer the question. Maybe the object is important, it's local information that's important for the task. Here, global-wise inspired when using image here. After pass the scene graph through a graph pooling, you just try to maximize this whole information, because maybe the whole information of the scene is important for the task. So you maximize this information. And here it's an approach to try to address the permutation invariance problem. What you try here is we calculated the distribution between the original scene graph here this S1, where the diagonal is like the mass, and between the original one and the augmented one. And you try to say, hey, S2, you should be as close as possible to S1 in order to address this permutation equivariance through a cross entropy loss. And here, we just add to the local loss, the local similarity also. So our results, we evaluated our project using the GQA dataset. And here we saw improvement in all metrics, and more specifically, the self-seeing get the better results, and the results is also improved when using a more expressive language encoder. Because in VQA normally you have the problem with language encoder that take all the information and try you have the bias between the question and the answer distribution. And here you saw the improvement, even when using a modern expressive language encoder. So when you evaluate on the types of question here to see if you have some bias, you saw a consistent improvement overall type of question. So you don't have like a bias depends on the question. You actually you have improvement overall question. That's important for the VQA test. So we also carry out ablation. The ablation was carried out as question to try to verify the functionality of our approach that go beyond the standard metrics. So here, first, does scene graph really matters for our approach? We try to make like unfavorable perturbation, like flip the image when the question is about relation. And you saw that there are more now it's like greater dropper is better because we are perturbing a lot the image. And you saw that our model pay more attention to the scene graph, while the baseline has probably another source of information, probably the question and the answer distribution, because sometimes even improve the results, what is strange. So here is to check whether the self-supervised loss is responsible for our improvement. And so we carry out we trained our baseline with augmentation to check if the augmentation or the self-supervised loss. And you saw that the augmentation actually harms the result. So the self-supervised loss probably they're responsible for improvement. Here's to check whether our approach is less biased and more robust. Here we just perturbed the node features without just slightly. With random noise over the scene graph and the question and both. And you saw that our model more robust. Here, even when using a more expressive language encoder, here it's important to point out that our model is only comparable to the baseline when we perturb the scene graph, because our model had a great drop and the scene graph doesn't have drop at all. So now it's like the same, because it's like another evidence that our model is paying more attention to the scene graph. So as a conclusion, we showed the impact of scene graph quality. The ideal one gets great performance, but when non-ideal, like practical way, you still have a room to improve. So we try a more practical framework where we try to utilize let's use a scene graph generator along with self-supervised learning, similarity maximization. And you saw that the similarity maximization improved the results by improve the visual information, what can be alternative to expensive model here because it's simple yet effective. And the improvement is keep consistent even when using a more expressive language encoder. So for future work, try to extend the dataset for more dataset, investigate alternative scene graph models to see how semantically responsive scene graph can change the results, to check if all kinds of scene graph derivatives from the image is enough. And because it's modular, you can try another architecture and another self-supervised learning techniques. So thank you.
Okay. I'm Xinwen here, and I'm here to present our work. What if the theory of examining counterfactual reasoning abilities of multimodal language models? So the project was mainly led by Zhang and Chen. Okay, so the motivation of this paper is actually quite easy. So to put it in one sentence, we rethink the counterfactual reasoning ability of the reasoning currently emerging very strong vision language models. And about the counterfactual reasoning? It's actually just think one more step. So for currently the reason, if we want to evaluate the understanding ability of vision language models, we actually evaluated mainly about vision question answering benchmarks, for example, VQA V2, right? And now we want to think one more step, and we want to ask models to try to think about it. What if the questions are given a preposition, or to likely to think about what will happen if something changes? What will this preposition to change the answer of the original question? For example, if there was a in the original visual question answering benchmark, there can be a very simple question like, given an image, you ask the model like, is there apple in this image, or is the apple rotten, or is the apple red? But we want to ask it like, what if the apple was stolen? Is there still apple here? Like this. So here is also another example, like, would the cat still be asleep? It was woken up. And so this paper is mainly benchmarking and no technical contributions. And given such motivation, we proposed a data set, counterfactual visual question answering, which contains about 2,000 images and question answer pairs. So here are more examples about it. So the original questions are like, how many places are there? Does there animals have claws? So all these things are so faithfully related to the image, but we want to make some challenge, make some attack to make the answer flip. And we make 3 types of presumptions. So there are 2 types of numerical questions. So the answer has to be a number. So about the numerical direct questions, so which means that the answer can be directly calculated by caption, like how many places are like the example in the top left corner. So the original question was to just count the place, and the presumption asked it to that what if 2 more places were added? So the answer is easy, just 1 + 2 = 3. And we also created some indirect numerical questions that ask it to use some other knowledge to solve the question, like the left bottom corner, like how many, the original question was how many cars are there in the image, which means how many cars are there in the TV. And we're asking it, what if the TV was off? And you know that when the TV is off, there's only one cat that is on the table, not in TV. So this is more indirect. And there are also some Boolean questions. So the answer is either yes or no. So the original question could be something related to the animal in the image, and we ask them, what if the animals are other kinds of animals, like they are not elephants but cats? What if they? How could it change the answer? And overall, we created around 2,000 images and question pairs. The original questions are all selected from the VQA V2 benchmark. And regarding how to create the new attack questions is quite easy. So we speed up the process with ChatGPT, most precisely GPT 3.5 Turbo. ChatGPT could make some mistakes, and so we manually inspected all the question and answer pairs, not much, just 2,001. So we manually inspected them and polished them to make sure that every question and the attack questions are valid, are natural, and they are suitable for benchmark. Okay, so now let's look for the results. So we mainly evaluated the most recent vision language models. There are neurosymbolic ones and neural ones. So the neurosymbolic ones we evaluated Viper GPT and with Proc, the best paper was CPR. And also some neural ones, or say they are purely neural networks like Instruct Blip, Blip2, and Lava. We also evaluated mini GPT-4, but the results relatively weaker, so we didn't put it here. And some side notes. So what are neurosymbolic models? To put it simply, so given it a question, it first uses a pure language model to convert the question into like a Python script, so Python code script. So it are given many smaller models like object detectors and smaller vision language models, and it uses the large language model to generate code and use the code to call the APIs of the relative smaller models to solve the question. And for the neural models, they are just purely generation models. So given the question, given the image, and it answers the questions. So overall, we found that neurosymbolic models are quite strong on these benchmarks, especially Viper GPT. And the most notable side is numeric direct side, because we know that they use Python code, so they never fails in calculating. For example, if you ask it 1 + 1 equals what, it must give you 2 because it uses Python. But for the neural ones, there can be mistakes. And another insight is that we found the current SOTA vision language neural vision language model Instruct Blip is actually quite strong on these counterfactual benchmarks, relatively strong. The absolute points are still quite low, but it stands out from other vision language models. Okay, so this is the same table. So, and generally speaking, they are overall quite weak on the counterfactual benchmark, and we want to raise the attention of the community to consider what if the vision language models to think one more step. Okay, to sum it up, we propose a new benchmark counterfactual vision question answering to ask the vision language models to think one more step before answering the questions. And we found that it's quite challenging. And currently, this work is quite preliminary, and we call for the efforts of the community to explore this direction. Okay, that's all. Thank you.
So the next talk is a pre-recorded video.
Hello everyone, I'm Jahagirdar from Hyderabad, and today I'll be presenting a work understanding video scenes through text, insights from text-based video question answering. Conversational AI encompasses a range of technologies designed to engage with humans in a manner that requires vast knowledge accumulated by humans over countless generations. Hello everyone, I'm Jahagirdar from Hyderabad, and today I'll be presenting a work understanding video scenes through text, insights from text-based video question answering. Conversation engage with humans in a manner that requires vast knowledge accumulated by humans over countless generations. To achieve this, researchers have introduced and cultivated various tasks and datasets. We can broadly differentiate these systems into reasoning over text-based information and reasoning over temporal-based information. The evolution of visual question answering technology began with methods focused solely on visual information without the need for text or temporal reasoning. However, advancements in the field have introduced tasks that require temporal reasoning, involving the integration of information from multiple frames to answer questions. Additionally, the prevalence of text information in our environment has led to a new direction in VQA, which incorporates scene text for better semantic interpretation. The need for systems that can reason over both temporal and textual information has led to development of two recent works, News Video QA and M4 Byte VQA. In this work, we explored these two recently introduced datasets. The News Video QA dataset contains question-answer pairs related to text and news videos, while M4 Byte VQA comprises question-answer pairs from diverse video categories such as blogging, traveling, etc. By exploring, we shed light on limitations of these datasets, such as the need for only textual information to answer questions and the need for only information from a single frame to answer questions. In order to understand both the datasets, we perform a data exploratory analysis. In this, we randomly select 100 question-answer pairs from M4 Byte VQA and News Video QA dataset to assess several aspects. Surprisingly, we found out that most questions in both datasets can be answered with information from a single frame and rely heavily on textual information. While these datasets have been designed for text-based video question answering task, the lack of questions requiring multi-modal information underscores the need for more advanced methods, especially for reasoning and knowledge-based questions beyond the capabilities of text-only methods. Seeing such heavy reliance of text in the BERT-QA, a text-only model. BERT-QA is a transformer-based encoder-only model, pre-trained on a large corpus and further fine-tuned on squad data. In all our experiments, we consider OCR tokens present in the videos as context to BERT-QA model. In this slide, we show the results of BERT-QA model on M4 Byte VQA dataset. To compare BERT-QA against the T5 Byte VQA model, we sample 1 frame per second and concatenate the OCR tokens from these frames to form the context. We take the BERT-QA large, fine-tune on squad QA, and further fine-tune it on M4 Byte VQA for 15 a box. It can be seen that it achieves comparable results to original T5 Byte VQA, which was a multimodal transformer-based method, whereas BERT-QA was just a text-only model. In this slide, we show the result of BERT-QA model on News Video QA dataset. Similar to M4 Byte VQA, it can be seen that BERT-QA outperforms the baselines provided. We perform multiple experiments on M4 Byte VQA, such as testing on questions that contain answers to their context, and also by testing the model on different types of questions such as easy, hard questions that require visual information and questions that require textual information. We also do out-of-domain training and testing among the two datasets. It can be seen that BERT-QA has a decent performance even when trained on one data and tested on another for both news video QA and M4 byte VQA datasets. Here we show some qualitative results. On news video QA dataset, it can be seen that with fine-tuning, BERT-QA can obtain correct answer if it is present in the context. Here we show some qualitative results on M4 byte VQA dataset. Here we show some results after out-of-domain training. It can be seen that by training the model on one source, only on source data, it was unable to obtain the correct answers. But by continued training on the target data, the BERT-QA model can obtain the desired output. More details are present in the paper and supplementary. For any queries, contact using the following mail ID. Thank you.
Hi everyone, I'm Mubin from Hyler, Korea, and can you hear me? Okay, I'm Mubin from Hyler, Korea, and I will present our work on multimodal temporal fusion for common sense video question answering. So yeah, we have a video and some like in some cases we have answer candidates and some cases it's just open-ended. And as it's discussed previously that there are some questions which are like counterfactual or predictive. These are much more challenging as compared to the evidence reasoning type questions, which really focus on like what is in the video or why someone did some action. So in this study, we also focused on how we can solve the problem of counterfactual questions or the predictive questions, because essentially these types of questions can be answered directly from the video. For example, if there is a question like what will happen if the cat will something like that. So actually the cat was doing something else, right? So I think we need to extract that information from the text itself. So in this figure, we can see the first part, like a car is running on an empty road and there is a picture. So we have achieved this kind of level, like the current, they can learn the unified representation from image, text, but how can we go move a step forward? Like what will happen if the car breaks down? So the answer is like, it will stop moving, but actually in the video, the car is never broke down, right? It was running. So how can we achieve that? So I think for that, we need to learn some like unified representation from text and the video. So it's like instilling some kind of imagination capabilities in the model. So we mainly hypothesized two things. Like, first of all, we need some fine-grained temporal context between the two different modalities. So we all know about there is a temporal context in the video, but there is also temporal context in the language, but it's not like it's just hidden in the words. You can say it's not explicit as in the video. So how can we use that? And the second one is like we need some fusion module, which basically fuses the both modalities at fine-grained level, not just computing the whole global context of the video and then the text and then doing some interaction. So like previously many methods did something like that. So we need some fine-grained fusion between the two modalities. So this figure is just, you can say, yeah, just overall illustration of what I'm trying to say. So previous methods did something like, because as it was discussed previously that so number of tokens in the video is quite huge as compared to the text. So if we just fuse them, like there are many methods. For example, they just replicate the text with the video. And some people also experimented with like, because you have like a short question and you have a long video. So there were also attempts to replicate the question tokens and then concat with the frames. But I think we can do something better. Like, how about learning to, you can say that expand the text along the temporal axis of the video, and in hopes that the model might learn some temporal text from the question as well. So idea is pretty simple, and yeah, it's inspired from, there was a work like 2 or 3 years ago about token learner. So it's quite inspired from that one. So basically, instead of replicating the question token, what we do is we expand the question tokens to match the temporal axis of the video. And after that, we add the temporal encoding to the question tokens. And then as these tokens match the dimensions match the video frames, so we just fuse them using really simple operations. And yep. And this can also further be used for various kind of audio features, even some object graphs or some frame features like, yep. I don't have much time now. Okay. So these are the 4 data sets we used to evaluate our approach, and the causal view had some more questions which we were like trying to focus on, like counterfactual or predictive. And yep. So on the causal VQA, we had pretty decent results as compared to the baseline models. And also the results were not that exciting on like MSVDQA, which is just based on descriptive or explanatory types of questions. And these are some results in HQA, again, not that surprising, but it was better than the previous baselines. These are some qualitative results. Yeah, so still the results are like not that impressive, but I think we need to focus towards learning some like combined representations. Yeah, thank you.
Hi everyone, my name is Chen. Today I will present our team's work on VQA therapy, exploring answer difference by grounding answers. Previous works have shown that a visual question can have different answers because of reasons like subjective or ambiguous visual questions. Our work aims to disentangle the vision problem from other possible reasons. For example, a visual question can have different answers because different visual content in an image is described. Or it can because the same visual content is described differently using different language. Our key contribution is that we are the first dataset that visually grounds each unique answer to each visual question. We named this the VQA answer therapy dataset. In total, it took 6 weeks to annotate 27,000 VQAs, and after quality control, we used around 5,800 of VQAs. Another key contribution is that we conducted fine-grained analysis on our dataset. One insight was about how prevalent is the multiple answer groundings. We found that our dataset shows that 16% of visual questions had answers leading to multiple answer groundings. Those multiple answer groundings can have different amounts of overlap, such as disjoint, intersected, and contented. We next examined when visual questions can have multiple answer groundings. Notably, visual questions about identifying location and visual questions related to reading text were more likely to have multiple answer groundings. On the other hand, visual questions that were difficult and visual questions related to recognizing color tend to have a single answer grounding. Our third contribution is that we propose 2 node tasks and evaluate their difficulty. The first task called the single answer grounding task. It aims to predict if a visual question will result in answers that all share the same groundings. If an algorithm excels in this task, it can notify users when there are uncertainty which visual evidence to consider and prompt users to clarify ambiguous visual questions. We benchmarked 2 VQA models. The VILG is fine-tuned on our dataset, and MPlug is tested in the zero-shot setting. We observed that model struggles to recognize which visual evidence have multiple valid answer groundings. Our second task, answers grounding, is to locate all answer groundings to a visual question. Success on this task can enable users of VQA solutions to better understand the varied reasoning process that can lead to different visual answers, making the models more expandable and trustworthy. More generally, this task also contributes to ethical AI by considering the diversity of possible answer groundings instead of only focusing on the answer grounding for the most common answer. For this task, we benchmarked 3 reference segmentation models. The sequence TR model is fine-tuned on our dataset, and SIM and UniNext models are tested in their short settings. Overall, that models struggle most to locate all valid answer groundings, particularly when there are multiple. We invite each of you to partake in our challenge to understand the diverse reasoning process that can lead to different answers and to design algorithms that value the diversity of answer groundings. Thank you.
We are running really behind schedules. So we have some preferences for like maybe you can have one. So there's a question that maybe the first offer or maybe the third presentation. So it's about counterfactual, and I'd like to use understanding this, and for me, counterfactual is a necessary condition to alter an outcome. So it must be related to the outcome. And the example that I gave with regard to the text or the vote of the TV, and I could say if the TV is turned off, the cat is infected and we have 0 text left. So how do you determine this kind of answers and how do you validate that?
Okay, so the evidence, so all the transforming the things what one of the actual rate didn't extract so complex outcomes such as it's the theory of the planetary theory and just the kind in the real world and also back. So yeah, this is also possible outcome for we see that actually when the third maybe a zero to that.
So the question, so we have the thing breakdown, and so we take agreement 10.5 for rates of people.
You are on Zoom, so yeah, we'll have to join. Okay.
That would be a very good idea. So you can try it on. Take one of these community Zoom on it as well.
Yeah, that's right.
That's the other one. Sometimes that's trouble. I've been able to.
Okay. Okay.
To get my computer and talk to Zoom. Yeah.
Yeah.
But I'm in the afternoon.
Yeah.
You can do it here.
I know you do the presentation or you can do something else.
You can turn the, oh no, I need it. I mean, I don't, no, actually, I don't need to see the slide.
Okay.
I only need to see the slide that everybody else.
Yeah, that's fine. Okay. The same thing, because we have some trouble, so
Yeah.
we might fix it and then.
Yeah, no, I actually prefer instead of all the other stuff that. All I see there what slide everybody.
Yeah.
I know it is there.
When I arrived on the world first from New York, I went to the world first. Are for joining.
You want to